Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Vapor Liquid Equilibrium. Now, having seen almost all details of non-ideality of vapor as well as the liquid phase, now we have come to a stage where we can apply those fundamental basic principles to realistic problems, right. So, now that is what we are going to start with today's lecture and then coming few lectures. So, today we start with the vapor liquid equilibrium problems. At equilibrium, what we know, the fundamentally very first week we realized that the chemical potential of each component in all coexisting phases which are at equilibrium are same. So, that is what our chemical potential of any component is same in all the phases that are coexisting and which are at equilibrium, that is what we have seen. So, and from there what we realized that not only chemical potential, fugacity of that particular component is also same in all the phases which are coexisting and equilibrium, that is what we have seen. And then we have this FIV is equals to FIL for vapor and liquid equilibrium, because now we are started discussing vapor liquid equilibrium problems. And then for a vapor phase, if it is having non-ideality, fugacity we can obtain by YI Phi Vp is equals to, and then if it is liquid phase, non-ideality can be brought into the picture by Xi gamma IL Fi naught, that is what we have already seen, right. So, that is both vapor and liquid phases are having non-ideality. So, then this equation we will be having. So, now if you wanted to know equilibrium composition, let us say Yi Xi you wanted to know, Yi Xi are nothing but the mole fraction of component I in the vapor phase which is in equilibrium with the liquid phase composition, right. So, the vapor phase composition is nothing but Yi and then liquid phase composition is nothing but Xi. These two are in equilibrium with each other. So, if you wanted to find out this Yi and Xi, you should know what is Phi V, right, that we have already seen how to obtain it for several cases. And then you should also know for the liquid phase what is gamma IL. This also we know depending on the information about the excess molar Gibbs energy. If you have that information, then the activity coefficient of component I you can find it out, right. And then pressure usually given or available, and that depends on the degrees of freedom, right. If it is two component binary mixture, two phase binary mixture, then degrees of freedom are 2, right. So, if you know any two independent variables, rest all other you can calculate without any difficulty, that is what says the Gibbs phase rule. So, let us say P and T are known for us, right. So, P is also known. So, Xi, Yi you have to calculate. So, now if you wanted to solve this equation not only about the information Phi V and then gamma IL, you also need to know information whatever is about this Fi naught, right. Because in the vapor phase or the gaseous phase, reference state are in general fixed in terms of ideal gas behavior, or with reference to the ideal gas behavior we define this fugacity of non-ideal vapor phase or gas phase. So, there we have directly pressure, but in the case of liquids the reference states are not one single reference state. So, different reference states are possible. So, Fi naught is nothing but the fugacity of component I in the liquid phase. This Fi naught what it is, if you know this one also, then we can solve this problem without any difficulty, right. So, Phi V is fugacity coefficient of ith component in the vapor phase, gamma IL is nothing but activity coefficient of ith component in the liquid phase. Now, in order to solve this problem you need to know reference state for Fi naught, and then you should also know composition dependent Phi V and then gamma IL, right. Reference state for Fi naught, it can be Lewis-Randall rule, it can be Henry's law as well, as we have seen, okay. So, now what we do for simplicity, we take the case of a ideal mixture, okay, that is both the liquid and vapor phases are obeying ideal behavior, and then start doing the problems, because from there it will be easy to develop and then bring in the non-ideality of the liquid phase and then non-ideality of the vapor phase simultaneously as a kind of gradual incremental order, right. So, now we take a case where the vapor phase is also ideal and then liquid phase is also ideal, right. Then under such conditions we can say whatever the principle that we are going to develop, that is known as the Raoult's law, that is what we are going to see. Now, consider the pressure as low. If the pressure is low, then only you can say that the vapor phase is ideal, and in addition to the low pressure, also assume that the intermolecular interactions are like interactions, unlike interactions, whatever the interaction that we have seen, all the interactions are same in the given liquid phase. So, that the liquid phase is also obeys a kind of ideal behavior, right. So, when you have the pressure is low and then all intermolecular forces are approximately same, then we can say vapor and liquid phases both can be treated as ideal. Now, if we take Lewis-Randall rule as reference state for liquid phase, because whatever this Fi, whatever this Yi phi v p is equals to xi gamma I L Fi naught. So, now here active ideal phases we have taken. So, the Figasty coefficient and activity coefficients are equals to 1 for both of them, then we get this equation as Yip is equals to xi Fi naught. Still, though the pressure is known, you have to find out xi and yi. So, but still you do not know Fi naught. So, for Fi naught we have to make a kind of a reference state. We have to consider a reference state. So, let us say if we take the Lewis-Randall rule as a kind of reference state for in order to define the Figasty of liquid phase at reference temperature pressure, right. So, if you take Lewis-Randall reference state, then Fi naught is nothing but what? According to Lewis-Randall rule, Fi naught is nothing but F pure I. That is what we have already seen. So, that means Fi naught is equals to F pure I and then gamma is equals to 1. So, then we have this Yip is equals to xi F pure I. Now, still you need to have some information about F pure I, then only you can further solve this problem easily. Otherwise, because Figasties are kind of much more related to the measurable temperature, pressure and then composition of the system, but still though it is better than the chemical potential, but still we need to have a kind of final form of this F pure I, then only we can solve this equation. So, now getting back to our Figasty calculation for a pure condensed phase, now it is F pure I is nothing but it is a pure component. This is the reference state. F pure I, it is a pure and then it is the liquid phase side. So, it is a condensed phase. For pure condensed phase, we have already seen this F pure I is equals to phi sat exponential of VIL by RT multiplied by P minus Pi sat. So, now here we have taken the pressure, total pressure as a very small low pressure kind of thing we have taken in order to have a kind of a ideal vapor phase. So, if the pressure is low, then obviously the Pi sat is going to be much lower than that one, right, because below the Pi sat we have the vapor phase and then above the Pi sat we can have a kind of condensed phase, etc. So, that is what the saturation equilibrium pressure means by, right. So, that means if you have both low P and then low Pi sat, this exponential of this term is going to be whatever in the parenthesis, this entire term is going to be very small. So, exponential of a very small quantity close to 0 is nothing but close to 1. So, that whatever the exponential of this entire term is nothing but it is very close to 1, that is also we have seen in one of the previous lectures. And then for ideal phases, this phi is anyway it is equals to 1, right. So, then what we get? F pure I is nothing but what is remaining in this term? Pi sat, right. So, at low P and low Pi sat, what we have? We can expect this exponential term close to 1 or very close to 1, and then for ideal gas Pi sat is equals to 1. So, then we have Fi naught is equals to Pi sat. So, that means this equation thus for pure condensed phase Figasty given by their saturation pressure. So, this equation whatever we have Yip is equals to xi Fi naught, that we can write as Yip is equals to xi Pi sat. We are taking let us say binary mixture and then two phases are there, obviously vapor and liquid. So, then degrees of freedom are nothing but 2. So, then if you fix the pressure and then temperature, you can find out this xi yi easily. That is what we are going to see, because P is given. If the T is also given, then if T is given, then you can know Pi sat through the Antoine equations. because those Antoine constants are almost known for all components. So, if you know those Antoine constants for a given component at a given temperature, you can find out the saturation pressure of that particular component, right. So, that means if the temperature is known, Pi sat is also known indirectly, right. So, now if you have a binary mixture A and B, so then two equations you will be having for A component, for B component. So, two equations, two unknowns would be there. So, those things you can comfortably calculate, and then under these conditions where this vapor and then liquid phase, both phases are ideal, then we came to final equation of this form, YIP is equals to Xi Pi sat is this is known as Raoult's law. This is known as Raoult's law. It is valid for ideal vapor and liquid solutions with Lewis-Randall reference state, with Lewis-Randall reference state. Remember, if you take for liquid phase as Henry's law as a kind of reference state, then Fi naught will become Hi naught or H1 Hi, whatever the Henry's law constant there for that particular component, that is the solubility of that particular component, that one be coming as a kind of additional term in the right hand side, not additional term, that is what we will be having Fi naught is equals to Hi. So, when you say Raoult's law, it is with reference to Lewis-Randall reference state, it is not with respect to the Henry's law reference state. Okay. So, as mentioned, Pi sat is dependent on the system temperature only, that is Antoine equation can be used to find it out without any difficulty. So, equation 4 what we can write for ideal liquid phase and then ideal vapor phase, we can write Yi is equals to some constant Ki Xi, and then Ki is nothing but P sat by P, and then Pi sat is nothing but it is a function of temperature. So, that means whatever this Ki that we are having, it is independent of the composition. If the both vapor and liquid phases are ideal, then this Ki is independent of a composition, that is what we can say, and then this is valid only when RL is applicable, right. So, this Ki is known as the K value of species I. It depends only on temperature and pressure of the system. It is independent of composition because of pure species that we are taking. So, this equation 5 is frequently used in hydrocarbon system where extensive data for K values are available. So, but this approach can be extended beyond limiting assumptions of RL also. That is obviously right, you are writing this YIP is equals to Xi Pi sat, right. If you have this non-ideality is also coming into the picture, then K is equals to Yi by Xi is nothing but Pi sat gamma IL divided by Phi V P, this is what you have. So, now here the Phi V and then gamma IL are again composition dependent. That is the only difference if you apply this K value principle for for the things beyond the assumption of Raoult's law, that is beyond the cases of beyond the cases of ideal vapor and then ideal liquid phase, then obviously this Phi V gamma IL would be coming into the picture. So, then obviously they will be composition dependent, that is the only additional thing, right. That is, in other words, for non-ideal systems, non-ideal vapor and then non-ideal liquid phase, if you wanted to find out this Ki values, this is going to be dependent on the composition also in addition to temperature and pressure. Okay. For the case of ideal behavior, it is this Ki value is going to be dependent only on pressure and temperature. For non-ideal system, it is also going to depend on the composition of the system. So, in other words, under the following two corrections, K remains independent of composition because both these corrections are based on pure species of properties. So, that is Lewis-Figasti rule used to correct for Figasti of real gases at high pressure, and then Poynting correction applied to LR reference states. K values are even extended to cases where ideal gas and ideal assumptions are no longer applied, but in such cases non-ideality of the system is included in K. Under such conditions, K depends on composition as well, as I mentioned here, right. For these cases, K values should be found either empirically or through Figacity and activity coefficient using equation 2, that is K is equals to Yi by Xi is equals to gamma IL Fi naught divided by phi V P. So, here since we are saying for non-ideal system, so Fi naught that you have to take as per the reference state. If you take a Lewis Randall reference state, then this Fi naught is going to be Pi sat. If you take the Henry's law as a kind of reference state, this Fi naught is going to be Hi. Okay, Henry's constant or the solubility of that component I, that is it. That is the only difference. Okay. But beyond the limiting assumptions of RL also it can be applicable under two conditions, or because under such conditions Lewis-Figasti rule used to correct Figasti of real gases at very higher pressures, and then Poynting correction applied to LR reference state. So, under these two conditions also this K is remains to be independent of composition, right. But if you have extended to the cases where ideal gas and then ideal solution is no longer applying, so then you have this Ki given by this one or defined by this one, where this Ki is dependent on composition as well in addition to the pressure and temperature. Now, what we do, we calculate, we make equilibrium composition of an ideal binary mixture of A and B that follows the Raoult's law. So, whatever YIP is equals to Xi Pi sat, that equation we have taken. So, that we are going to find out what is Yi, what is Xi, how to find out that this Yi or Xi are both at a given temperature and pressure, that is what we are going to see now. Okay. So, we start with binary system, so that it can be easy to develop on this ideal behavior and then bring in the non-ideality in the later cases. Consider a binary mixture of species A and B, then for two components this YIP is equals to Xi Pi sat, we can write it as YAP is equals to Xa Pi sat, YBP is equals to XB Pb sat. Now, if you add them together, Ya plus YBP is equals to nothing but P, because Ya plus Yb is equals to 1 for a binary mixture. So, P is equals to, left hand side is P and then right hand side Xa Pi sat plus Xb Pb sat. So, now here what we understand from this equation number 8, if the pressure and then temperature are known, you can find out Xi without any difficulty, because at a given temperature Pi sat, Pb sat can be known and then P is given. So, Xa you can find it out. Now, if you substitute this particular P in equation number 6, then you have this Ya Xa Pi sat plus 1 minus Xa Pb sat is equals to Xa Pi sat. So, that means Ya is equals to Xa Pi sat divided by Xa Pi sat plus 1 minus Xa Pb sat, that is what you can have now here, right. At a given pressure and temperature, this Xa you have already found out from this equation number 8, and then Xa is already known. So, then you using the equation number 9 you can find out Ya. So, for simply given pressure and temperature, you are comfortably able to calculate equilibrium composition of this vapor liquid system for a vapor liquid binary system, because degrees of freedom is 2 for this binary system having 2 phases. So, the degrees of freedom, so 2, that means 2 independent variables we are fixing, we can fix. So, let us say if I fix pressure and temperature, then remaining 2 independent variables, that is Ya you can find out and then Xa also you can find out. So, that is what we can do from this equation number 8 and 9, right. Not only the pressure and temperature, you can fix anything. Let us say P and Ya you fix, then T and Xa you can find out, or P and Xa you fix, then T and Ya you can find out without any difficulty. We are going to solve a few problems as well on this. So, these equations 8 and 9 would be help us in constructing the phase diagram. Phase diagram in the sense, at a given temperature and pressure, if you have this binary system and then there is a kind of vapor liquid equilibrium is existing. So, what kind of phases are existing at given temperature pressure and then under what composition kind of phase is pure phase, pure vapor phase, pure liquid phase, or a binary phase is existing, all those kind of things we can construct from these equations, these two equations. That is what we are going to do for ideal liquid and ideal vapor phase today, and then later on we take the non-ideal liquid phases also coming into the picture. So, now from equation 8 what we understand, So, we have this rearrangement of the same equation number 8, P is equals to x a multiplied by P a sat minus P b sat plus P b sat. That means, x a is equals to P minus P b sat divided by P a sat minus P b sat, that is straightforward. But what is the important thing to see, this P versus x a is a linear relation from this equation number 6, is not it? It is a linear relation, and then it is having a slope of nothing but P a sat minus P b sat, right. And then when x a is equals to 1, whatever the P is there, that is nothing but P a sat, and then when x a is equals to 0, whatever the P is nothing but that is P b sat, right. So, this P versus x a curve for an ideal liquid phase, it is going to be linear straight line like this. So, that is what we have to understand from here, because now let us say when you are constructing phase diagram. So, P x a information or the curve you already drawn it, right. So, now we understand at higher pressures liquid phases would be there, liquid or condensed phase is going to exist. So, above whatever the composition you take, this point, any point if you take this composition, right. So, if the composition and the pressure for a given composition of x a, if the pressure is more than is going beyond this straight line. So, then what we can have, we can have a kind of a subcooled liquid, only liquid phase existing, right. So, that is what we can say, and then vapor phase is going to be there below this line, but not entire amount, but there may be a kind of region of where both vapor and liquid phases may be coexisting. That information we can understand if you plot this P versus Y a, right. P versus Y a if you plot, it is not going to be linear like this. Now, equations 8 if you rewrite like this, you can clearly understand this is y is equals to m x plus c form, it is a linear equation. But equation number 9, P versus Y a, it is not linear, it is not linear. So, that is the important difference one has to realize here. Though vapor phase is also ideal, but P versus composition, P versus Y a curve is not linear here, whereas liquid phase is ideal, but P versus x a is a linear curve. So, let us say P versus Y a curve, it is having some form like this. So, now this is Y a is equals to 1. So, now here in this region, whatever this between the two enclosed region, whatever is there, in these two regions we are going to have a kind of a binary mixture, that is both vapor and liquid are coexisting, right. Below this P Y a curve, so because this is P Y a curve, so below this one we will be having superheated vapor, only vapor phase we are going to have, and then above this P x a curve we are going to have only subcooled liquid. In between we are going to have both the vapor and liquid, but they are at equilibrium. Okay. So, this exactly the same thing from this information of equation 8 and 9 I have redrawn here. So, this is what we have, right. So, at a constant temperature I am trying to draw P x y diagram. P x y diagram. So, at system pressure this is what we are having. So, pressure we are changing now, pressure and then composition we are changing and then trying to find out at constant temperature how this curve look like. So, this P versus x a is a straight line that we already mentioned. So, this is what one, this is the one with a slope we are having P b sat minus P a sat. Okay. So, this P x a curve we know that it is a linear, and then we know the slope of this curve is nothing but P a sat minus P b sat, that is what we understand. And then P y a curve is not a linear one, it is a non-linear one, and then that is having shape like this, that equation number 9, whatever this equation, right. So, then this is what we are having, this known as a P y a curve and this is P x a curve. So, any combination of this composition x a y a, if the pressure is above this the pressure is falling above this PXA line. So, then we can have the system only subcooled liquid, right. Or if the pressure and then composition combination is such a way that if the data point is falling above this PXA curve, then we can say that only subcooled liquid single phase is existing. Or for a combination of pressure and then composition, any combination of pressure and composition, if the data point is following below this PYA curve, that means we are having only superheated vapor phase, right. And then let us say if you have a combination of pressure and composition such a way that the data point is falling in this encapsulation between these two curves, that is PXA and then PYA curve, then we can say both vapor and liquid phases are coexisting and they are at equilibrium. That is what we can say, right. So, now this PXA curve is also known as a kind of bubble point curve. This also known as a kind of bubble point curve, because let us say at certain composition XA, the pressure, if you gradually decrease the pressure, let us say initially the composition is having some value here and then pressure you are gradually decreasing. So, when the pressure comes out to this point where it touches the PXA curve, that is the point where the first bubble has formed. Above it, it is only liquid is there, and then the pressure comes to the point where it touches this PXA line, that is the point where the first bubble forms with certain YA value. Otherwise, initially it was only XA value it is having, right. So, that is what. So, so that is the point, first bubble forms, okay, and then as you that is the reason this PXA curve is also known as the bubble point curve, and then whatever the PYA curve is there, it is also known as the dew point curve, because let us say any composition YA you are having here, and then gradually isothermally at constant temperature you are increasing the pressure. So, initially it was superheated vapor, and then as gradually increasing the pressure, so condensed fat will start forming at certain point. So, the pressure when it touches this PYA curve, so that is the point where the first dew is forming from this vapor phase, right. So, liquid started forming and then further increase. So, then there will be a kind of condition where both vapor and liquid should be there, and then after crossing this PXA curve, again only liquid phase, subcooled liquid phase is going to be there. So, that is the reason PYA curve is also known as the dew point curve, because on this point the first point where the first dew is forming, So, that is the reason dew point curve, it is also known as the dew point curve, right. So, now at certain system pressure P system, let us say if you have a kind of draw a horizontal line, so that is known as the tie line. Tie line in the sense it ties the composition of a vapor phase and then liquid phase which are at equilibrium. So, that is the reason they are known as the tie line. So, and then if ZA is the kind of a feed composition, the point which joins this P system and ZA. So, now here you can have a kind of segmenting this line in two parts. Whatever this tie line is there, for this combination of P system and ZA, this tie line is segmented in two parts, right. So, one is this part, okay, which is known as line segment V, and then this is the other part which is known as the line segment L. Line segment V here in the left hand side, line segment L in the right hand side. So, this will also give the ratio, if you take the proportion of the amount of vapor to the amount of liquid is given by the ratio between this line segments V by L. So, now this phase diagram, not only from this phase diagram picture, it is not only that we get the what kind of phase is existing, whether subcooled liquid or the superheated vapor or both phases are existing. Not only that information, we can also find out the composition at a given temperature and pressure. Not only that composition, equilibrium composition, but also we know what is the ratio between the amount of vapor formed to the amount of liquid that is formed at given system pressure and then composition. That is also we can find out. Okay. So, this is what about the phase diagram. So, this is known as a kind of phase diagram, because now it says which phase is existing, at what composition it is existing, and what is the corresponding pressure, and all that information we know. It is we are doing at the T constant T isothermal system, but by changing the pressure. You can also have the Txy curves also, it is possible, right. So, now if you have a Txy curve, so then what happens, the liquid phase would be at the bottom, because at the lower temperature liquid phase would be there, and then at the higher temperature, larger temperature, beyond that Ty curve, you will be having vapor phase, superheated vapor phase would be having. So, those kind of things you might already be knowing through your undergraduate courses, or you can construct Txy diagrams also simultaneously using the same equations. Using the same equations are written those two equations here. That I leave it to you to do yourself as a kind of a self exercise problem. So, all this is provided as a kind of notes here. So, if you know the liquid mole fraction and temperature, then P can be calculated by this equation. Once P is known, so at a given temperature, P sat can also be known, and then Xa is known for this case, let us say, then you can find out Ya using this expression, right. That is what we are doing. Now, linear relationship between pressure and then liquid phase we have seen, that is known as the Pxa curve or Pxa line. If it is linear, then we call Pxa line for ideal liquid system. Let us say if you have a kind of non-ideal liquid system, then whatever the Pxa line is there, that is not going to be linear, as we are going to see later course. Okay. Phase diagram useful for identifying thermodynamic state of a binary mixture, that is, these diagrams tell us what phase or phases are present, and in the two phase region composition of the liquid and vapor phases, as well their relative amounts, that is Xi Yi, not only Xi Yi, also V by L information also we get, how much amount vapor is present relative to the liquid amount, all those things also we can find out from this diagram. So, from this phase diagram we understand there is a subcooled liquid phase, there is a superheated vapor phase, and there is a combination of two phases, that is the liquid phase in equilibrium with the vapor phase, that is the area constraint between Pxa and then Pya curves. So, by convention, obviously lighter component, or that one boils more easily, is labeled as a kind of more volatile component, and then more volatile components are given convention A Xa if you have a binary mixture of A and B. So, A is more relative to the B. So, whatever this curve, if you have drawn with respect to mole fraction of A, that means in the mixture A is more volatile than the B, that is what it means. At high pressure subcooled liquid and at low pressure superheated vapor exist in these Pxy diagrams. In between these two regions we observe a two phase region where mixture is in vapor liquid equilibrium. In this case composition and an amount of each phase can also be determined from the phase diagram, as I already explained. Now, consider a system with overall composition Za and pressure P system. At this pressure one can draw a tie line. At the P system, if you draw a horizontal line, so that line that intersects both Pxa curve and then Pya curve is known as the tie line, because it ties the composition at that system pressure P system. So, this line is called the tie line because it ties together the composition of liquid and vapor phases which are coexisting and which are at equilibrium. It is horizontal because the pressure of the liquid and vapor are the same. This is what we have seen, and at the beginning when we are discussing the defining the equilibrium of a system with respect to three processes, mechanical equilibrium, thermal equilibrium and chemical equilibrium. If the system to be said as a kind of equilibrium, the system has to be in equilibrium with respect to all internal 3 equilibrium processes, internally equilibrium with respect to pressure, with respect to the temperature and with respect to the chemical potential. So, we know that for a system to be mechanically equilibrium, at mechanical equilibrium pressure has to be same. So, that is the reason this horizontal line, tie line whatever is there, it is horizontal. Liquid mole fraction is XA equilibrium, which is obtained from the intersection of the tie line with the liquid line on the left. This on the left is a kind of relative kind of thing. If you write Txy, then it is going to be other side. Okay. So, that is simply intersection of the tie line with the Pxa curve. Okay. And then similarly, vapor mole fraction is Ya equilibrium. It is obtained from the intersection with the vapor line, that is on the Pya curve. Here in the case it is dew point curve. It is also known as dew point curve. And then more volatile species A has a higher concentration in the vapor phase, obviously, because it is more volatile. So, it can easily boil and it can easily vaporize and go into the vapor phase. And then by lever rule, amount of vapor to liquid in the system is given by the ratio of line segment from feed compression to opposite curve, as shown in the figure, that V by L, line segment V and then line segment L. If you take these ratios, that you will get relative amount of vapor to liquid in the system at that system pressure. Liquid mole fraction versus pressure line is often termed as bubble point curve, because if we start at high pressure and decrease the system pressure at constant temperature, this curve marks the pressure at which the first bubble of vapor forms. Bubble compression can be found where the tie line intersects Pya curve. And then similarly, vapor mole fraction versus pressure curve is known as the dew point curve, because this mark when the first drop of liquid forms when a superheated vapor mixture is isothermally compressed by increasing the pressure. And then equations 8 and 9 can be generalized to a system with m component as follows, that is P is equals to sigma xi Pi sat, I is equals to 1 to m. So, this is given as a notes, as I already explained all these points in the Pxy curve diagram itself. So, if you know the relation between xi and p for m number of components, so then you can also find out yi for those m number of components by using yi is equals to xi Pi sat divided by sigma xi Pi sat. Now, quickly what we do, we take a few simple problems to understand these things, then we go into non-ideal behavior of a vapor liquid system. So, before going to the problems, what we do, we see a few common types of VLE calculations. So, VLE calculations are 4 types. You can have a kind of this T known and then P known kind of system. If T known and then Xi is also known, then those things are known as the bubble point calculations, where you can find out yi and then p. Pi sat is said because T is known. Then if p known and then xi known, then also it is known as the bubble point calculation, where you can find out yi T. Pi sat unknown. So, by trial and error you can find out these things, temperature and then Pi sat, that is what we are going to do now anyway. Then if T known and then yi known, it is known as the dew point calculations, where you will be finding xi and p. If p is known and then yi is known, then also it is known as a kind of dew point calculation, where you will be finding xi and t. If you are finding, simply to memorize or simply to have a kind of as a kind of simple principles to realize whether it is a dew point calculation or by bubble point calculation. If you are finding out xi values, then it is a dew point calculation. If you are finding yi values, it is bubble point calculations. Fine. So, example 1, bubble point calculation with P known, right. So, yi T we are going to find out. Consider a system with liquid containing 30% N-pentane, 30% cyclohexane, 20% N-hexane and 20% N-heptane at 1 bar. Pressure is given 1 bar, it is low pressure. So, we can say that the vapor phase is ideal phase, though it is not given. Determine the temperature at which this liquid develops the first bubble or vapor and what is vapor composition. So, Xi and P are given, liquid mole fractions are given, 4 components. Multi-component system we are doing 4 components, okay, but it is a 2-phase system, okay, 2-phase but multi-component, and then ideal phases. So, calculate Yi and T here. Since components in the system are chemically similar, one can assume ideal solution, and then since pressure is low, one can also assume ideal gas assumption for a vapor phase. Then we have Yip is equals to Xi PA sat, right. You need to find out Yi. P is given, Xi is given. So, Yi you can find out only if you know PA sat, and then PA sat you can know only if you know the temperature, which is not given, right. So, what we do, we write this equation for 4 components like this and then add them together. When you add them together, sigma Yip is nothing but P, and then sigma Xi PA sat is nothing but x1 P1 sat plus x2 P2 sat plus x3 P3 sat plus x4 P4 sat. This is what we have, right. So, now PA sat can be found from Antony equation. So, ln PA sat in bars is nothing but Ai minus Bi by T plus Ci. T is in Kelvin. This Ai, Bi and then Ci are nothing but Antony constants. They are available for almost all components in standard chemical engineering thermodynamics books, right. So, now this equation, if you substitute in our previous equation, P is equals to sigma Xi Pi sat for each component, then expand. So, you have this equation. In place of PA sat, what we are writing? PA sat is nothing but exponential of Ai minus Bi by T in Kelvin Ci. This is what we are writing. This is for the component 1, this is for the component 2, this is for the component 3 and this is for the component 4, and these are nothing but x1, x2, x3, x4, and then P is nothing but 1 bar, it is given. So, now in this equation, except this temperature, everything is known. These are nothing but Ai, Bi and then this Ci for component 1. Similarly, for component 2 also these are available. I have tabulated in this next slide. So, this equation you can solve, you can find out T, that is the only unknown, right. So, by trial and error you can solve this equation and then you will find it out as 333 Kelvin, right. So, now the temperature is known. Out of Yi and T, T is known, only Yi is remaining. So, Yi you can find it out using Yip is equals to Xi PA sat. Xi is given, Xi is given, P is also given. Now, temperature we already find it out as if we found as 333 Kelvin. At 333 Kelvin you can find out the PA sat for each component using this Antony equation, calculating back. So, for this N-pentane, cyclohexane, N-hexane and heptane, this A, B, C or Ai, Bi, Ci values are given. At 333 Kelvin, if you find it out PA sat for each of these component, you get these values in bar. So, if you substitute this PA sat in this equation 1, then Yi is nothing but Xi PA sat by P. So, then you get these Y1, Y2, Y3, Y4 values as like this, right. So, simply P and Xi is given. So, Yi and T you able to calculate without any difficulty here. Okay. Now, we take a similar problem. So, here dew point calculation with P known. So, that is P and that is you have to find out xi and t. Xi and t you have to find out, P and yi are given. So, now consider a system with vapor containing, this is vapor mixture. So, y1 is 0.3, y2 is 0.3, y3 is 0.2 and y4 is 0.4, 4 components, P is 1 bar. P and yi are given, x and ti you have to find out. In the previous problem, P and xi were given, t and yy you have find out. So, now here P and yi are given, t and xi you are finding out, that is the difference, same equations. And then assume ideal gas because the pressure is low and then these components are chemically similar. So, then you can assume the liquid phase is also ideal. If the chemicals are similar in nature, so then their interactions are going to be similar. If the interactions are similar, so then we can say that is the ideal liquid solution. So, the same equation we have to use, yip is equals to xi pi sat. So, now xi you have to find out. So, xi is equals to yip by pi sat. P is given, yi is given, but pi sat is not given. So, if you know the temperature, then you can know pi sat, but the temperature also not given. So, temperature you have to find out, then only you can find out xi. So, temperature how you can find out? This equation you can write sigma xi is equals to sigma yip by pi sat. This is what we can write, sigma xi is equals to 1. So, that means if you extend 1 is equals to y1 P by P1 sat plus y2 P by P2 sat plus y3 P by P3 sat and then y4 and then plus y4 P by P4 sat. So, P is common, that you can take it as a common. So, now Pi sat you can find out from the Anton equation like this. So, this is the nothing but Pi sat using the Anton equation. This is P1 sat, this is P2 sat and this is P3 sat and this is P4 sat. This is y1, this is y2, this is y3, this is y4 and this is pressure is 1 bar. So, in this equation also except the temperature everything is known. So, here also what you can do, you can do the trial and error approach and then find out this temperature as 349 Kelvin. So, now the temperature is known now. Out of T and xi calculations, T already you got. So, xi is very straightforward because xi is nothing but yip by pi sat. So, now if T is known, so then this pi sat is known through the Anton equation. So, P1 sat you can find it out, P2 sat, P3 sat and then P4 sat you can find it out. Right. This Anton constants etc. are same like in a previous problem because same components are there. So, I have not written them back. So, once you find out this pi sat for 4 components at 349 Kelvin, then xi you can find it out using this equation, xi is equals to yip by pi sat as x1, x2, x3, x4 as these values, straightforward and simple. So, quickly look at it one last problem for the day. A compressed liquid feed stream containing equimolar mixture of n-pentane and n-hexane flow into a flash unit at a flow rate f. At steady state 33.3% of feed stream is vaporized and leaves the drum as a vapor stream with flow rate V. The rest leaves as a liquid with flow rate L. If flash temperature is 20 degrees centigrade, what is the pressure required? What are the composition of the liquid and vapor exit stream? Right. So, previous 2 examples were finding the equilibrium composition and temperature, those things we have seen. Now, here we are going to do find out, in addition to this composition, we are going to find out the relative amounts of this V to L, that is also we are going to find out here. So, pictorially we have a flash unit in which we are sending these 2 components, right, having equimolar composition. In the unit temperature is maintained 20 degrees centigrade. So, then a flash has to be carried out. So, then certain pressure has to be given at this temperature, so that the separation of vapor liquid takes place. So, how much the pressure is required, that is what we have to calculate, right. So, when the vapor is going out, so what is this Ya after the flash, the vapor composition is how much, and then what is the liquid, this Xa composition, that liquid composition is how much, that we have to find out, right. This amount wise V by F is given, and then L by F is also given. 1/3 of the feed is going into the vapor phase, and then 2/3 of the feed is going into the liquid phase after this and the flash operation taking place in this flash unit, right. So, Ya and Xa, and then V and L also we have to find out. So, material balance for component A, if you do, XAF is equals to YAV plus XAL, right, and then assume ideal gas. So, then YAP is equals to XAPSat, then substitute this equation number 2 in equation number 1. So, then XAF F is equals to YAV is, Ya is nothing but XAPSat by P V plus XAL, right. So, this feed composition whatever is there, that we are indicating XAF. So, that is the reason XAF we are writing here, right. In the right hand side what you can do, you can take Xa common, which is there in both of the components, both of the terms in the right hand side. So, Xa multiplied by PSat by P V plus L, this is what we have, right. That means, Xa is equals to XAF divided by PSat by P V by F plus L by F, this is what we have. So, here now XAF is given as 0.5 equimolar feed composition, and then V by F is given as 1 by 3, L by F is given as 2 by 3. Now, only thing you know, if you know PSat, then and then P, then you can know find out Xa. PSat you can find out because temperature is given 20 degrees centigrade, but P is not given. So, you cannot solve this equation directly. So, what we do? Similarly, we write for the second component. Second component XB, if you write similarly, you get XB is equals to XBF divided by PBsat by P V by F plus L by F. This L by F is given, V by F is given, XBF is given. PBsat you can find out because T is given. So, P is not known. Here also you cannot find out Xa directly. So, but what you do, you have two equations, only one unknown. If you add them together, you can find out easily. So, when you add them together, Xa plus Xb in the left hand side, that is nothing but 1. So, 1 is equals to addition of these right hand side terms. So, at 20 degrees centigrade for this N-pentane and N-hexane system, Ai, Bi, Ci values are given, Antoine constants are given, or we can find out from the chemical engineering thermodynamics books. Then corresponding PSat you can find it out, you can find them as 0.56 and 0.16 bar respectively. So, PSat is also known. So, simply in this equation whatever 1 is equals to XAF divided by PSat divided by P V by F plus L by F plus XBF divided by PBsat by P V by F plus L by F. In this equation now, PSat, PBsat all are also known in addition to the rest everything. Rest everything, that is V by F, L by F are known, XAF, XBF are also known, PSat, PBsat you just calculated. So, only unknown is P. So, that if you substitute here XAF, XBF are 0.5, V by F are 1 by 3 and then L by F are 2 by 3. So, they are given. PSat is 0.56, PBsat is 0.16. So, this equation except P everything is known. So, P you can find it out, it comes out to be as 0.32 bar. So, that means when this equimolar mixture you take in a flash unit at 20 degree centigrade, in order to have 1/3 of this feed into the vapor phase and 2/3 of the feed into the liquid phase as a kind of separate two separate phases, then you have to apply a pressure of 0.32 bar. 0.32 bar pressure you have to apply. So, then once P is known, so XAF you can easily find out from this equation, that is XA is equals to XAF divided by PSat by P V by F plus L by F, because these things are given. P you just found it as a 0.32 bar. So, it comes out to be 0.4 and then Ya comes out to be 0.7. Similarly, because if once XA is known, then Ya is nothing but XA sat PSat divided by P. So, that comes out to be 0.7, right. This is how we can apply these principles to solve any vapor liquid problems. Today we have taken only the cases where both the phases are ideal phases. In the next lecture we will be taking the cases where start with a case where the liquid phase having non-ideality, positive deviation from ideality, negative deviation from the ideality, those things we incorporate in liquid phase. Then again for those cases we are going to draw the phase diagram and then we are going to solve a few problems in the next lecture. References for this lecture are given here, but henceforth the entire course, all the notes would be prepared from this reference book. That is for this VLE, LLE and VLLE, SLE cases, the entire notes is going to be prepared from this lecture notes, that is Engineering and Chemical Thermodynamics by Koretsky, though there are many other books available which can serve as a kind of better reference. Thank you.